Okay, welcome everyone to the School of Physics and Astronomy and Center for Detectors seminar. I'd like to introduce today's speaker. We have the room until 1:50 or so, 1:55. So hopefully our speaker will finish talking in about 45 minutes. We'll have time for questions. Today's speaker is Dr. Roger O'Brien. He's from NASA JPL Caltech, where the weather is sometimes as good as here, sometimes not as good. But he spent a lot of time at the South Pole, so we try to make him feel at home today. He's doing a postdoc with Professor Jamie Bach, and he got his PhD from Berkeley with Professor Adrian Lee. He got his bachelor's at Caltech again in 2001. So, Dr. Roger O'Brien.
So thanks for the intro and the invitation to speak today. In case you missed it, I'm Roger O'Brien from NASA's Jet Propulsion Laboratory at Caltech, where for the past 5 years or so I've been sort of coordinating the efforts to get our detectors, some of what you're seeing here, into a variety of CMB experiments, BICEP, Keck array, and Spider being some of them. And these are detectors that sort of very generally observe in the sub-millimeter range. And in fact, these science goals we'll be talking about have been very directly enabled by a revolution in this technology that's occurred over the past decade that I've been lucky enough to play a role in. And I actually think this is some of the most fascinating light to study in the universe, for the simple reason that it lets you look at the most distant parts of the observable universe. It takes time to get here. So you're also looking at the most ancient images of our universe, often corresponding to physics that occurs at some of the highest conceivable temperatures. And the reason this is in the sub-millimeter band is because that light traveling to us must traverse through the stretching space of an expanding universe that stretches out the wavelength of the light little by little over time. So it gets pushed from perhaps the near IR down into the millimeter range, right? So that's what pushes it into this weird range, why it's important. So we're going to be talking about some pretty big science goals here. What's the physics behind inflation? How's that related to grand unification? What are the neutrino masses? What's the neutrino mass hierarchy? These are open questions in particle physics. And then towards the end, I'll talk a little about lower redshift phenomena, reionization. I don't know if I'll have time to talk about dark energy, but nonetheless have interesting ideas about that. So let's start with the first of these. Inflation, as I'll point out in a second here, is a faint signal, but prevalent on large angular scales. And so what this means is you don't need a giant dish to resolve such a thing. It can be a small aperture camera, and in fact, that might even make sense, might be smart, because that means you can put many of these low-cost instruments on the ground and really amp up your sensitivity aggressively to chase down what is, after all, a faint signal. The catch is to keep up with these ambitions, you need a detector technology that's highly scalable. Right? So this is the history of our universe in timeline form. Big Bang at left, modern times at right, 14 billion years later. This increasing vertical scaling here is meant to reflect that expansion that I was just describing, that stretching of space. And apparently most of it occurred in the first fraction of a second during inflation. This was this period of, we think, superluminal expansion. When that ended, the fields driving it should have decayed into a bath of hot ionized matter, which would then cool through the subsequent but more genteel expansion, the stretching of space, cooling the light by stretching out the wavelength. And eventually, 400,000 years later, things were cool enough for atoms to form for the very first time, what we call this event recombination. And when that occurred, the light that had been holding matter ionized was abruptly released. That's the CMB. And we can still see that. It's the cosmic microwave background. We can still see it in our telescopes 14 billion years later, albeit redshifted by subsequent expansion here, out into the millimeter spectral regime. So that's responsible for its famous 2.7 Kelvin temperature and a black body spectrum peaking at around 150 gigahertz. Right? So inflation should amplify quantum fluctuations to the background gravitational metric out to cosmic scales, or so we suspect. These cartoons are depicting that. The top one is supposed to be gravitational waves, or what a mathematician might call tensor mode. These have not been definitively detected yet, although many of us are searching for them. The lower one depicts gravitational wells that would subsequently see galactic structure formation. In the early universe, however, they trigger and drive sound waves, right? Acoustic oscillations, or what I'm labeling here as density waves. And that gives rise to hot and cold regions, and most importantly, hot and cold regions across the surface of last scattering, as we call it. This is where the microwave background is produced. Right, so if you have a map of the CMB, and if you subtract away that 2.7 Kelvin average, as well as some foregrounds of the galaxy, you'd see spots like this. This is a map from Planck, an ESA satellite that was observing them recently. These spots here, hot and cool, also trace the over and undense regions. Right? So these are the seeds of galaxies. In many ways, it's a baby photo of our universe. Right? If the universe were an 80-year-old man or a woman, this would have been taken in the first few hours of its life. You can summarize most of the information in these maps into what we call an angular power spectrum. Right, so this is plotting on the vertical axis the variance of spot temperature in units of microcase squared versus the reciprocal spot size. So that means that large spots are over here, right? So these large orangish regions or these large bluish regions. Then, of course, the finer things are over on the right-hand side, the little dots in there. In fact, the really fine scale stuff is from other larger aperture experiments in the ground. Right, so you can think of it as a Fourier transform of this map, and it has the fingerprints of inflation all over it. You'll note that there's these peaks here. Right, those are waves, modes, sound wave modes that are just reaching full compression or rarefication of recombination, and they give rise to the most prominent spots in this map. And thanks to something like inflation synchronizing them, you get this harmonic-looking pattern here. Not only that, but the left-right positions of the peaks can be used to measure the flatness or curvature of our universe on the largest scales. It's consistent with flat, which is another prediction of that rapid expansion from inflation. So this map is also polarized. And to get a sense of that, just consider one sound wave going from left to right. It has alternating high and low pressure planes, hot and cold planes. Right? So an electron right at last scattering, about to join an atom and scatter away CMP photons, it will witness hot coming, let's say, from left to right, and then its own plane a little bit cooler. And it's kind of like the afternoon sky where the sun's illuminating on one side. It scatters light towards us. That is polarized, right? Partially so. But here's the rub. It has to be polarized parallel or perpendicular to the left-right direction of this wave because it doesn't know any other direction, or more to the point to the temperature gradient there. Right? So if that relationship is preserved under mirroring, under parity, right? Parallel or perpendicular. Right? So if you actually superpose many of these modes, which is I'm doing on the right here, you will get characteristic circular and then asterisk-looking patterns. I guess I cut off the bottom of there. But those themselves are preserved under parity. Right? The gravitational wave, on the other hand, has no such restriction. So as it's going from left to right, right, it's compressing and stretching space on orthogonal axes, but maybe it's rotated in such a way where you see hot, kind of a one oblique angle where it's being compressed, and then where it's being stretched, maybe it's cooled here. Right? So now the electrons, they can be shaken in some arbitrary direction. The polarization is no longer restricted. It can go into either the even symmetry E mode pattern or the odd symmetry B mode pattern seen here that have this characteristic kind of pinwheel pattern. Right, that flips chirality when you look at it through a mirror. Right, so that's in some senses the telltale sign of a gravitational wave, and this is what they should look like in angular power space. Right, so this is a Fourier transform again. So again, reciprocal spot size on horizontal, big scales, tiny scales. Vertical axis, now the variance of excess polarization power in one direction versus the other, but still in microcase squared. So temperature will be way off the top of the charts. E modes here are red. It's been seen by numerous experiments. Of course, this is just a theory computation. We'll come back. I should point some of these dashed lines here are no longer true, so the field is changing rapidly. We'll come back and talk about the green curve in a second. Blue here are a range of possibilities of a B mode spectrum from gravitational waves. They're corresponding to different values of R, which we call the tensor scalar ratio, the ratio power from the gravitational waves versus the wells. It's of interest because if you measure that, you can infer how hot inflation was. There's two key features here. Note that this is peaking here at L of 80. If you go to the top, you can see it corresponds to maybe a couple degrees across, which is humongous, right? The full moon is like a half degree on the side, right? So you don't need a lot of resolving power to see such a thing, right? And in fact, if that's your priority, then it behooves you to build an instrument with just enough resolution to get the job done without going overboard, because after all, this is quite faint, down by orders of magnitude from the E modes and further yet from temperature. Right, so you need gobs of detectors in the sky at once to have a chance of seeing anything here. Right, so that's the strategy. Small telescopes that you can scale up. This is the team, currently based out of Harvard, Stanford, Caltech, where I am, University of Minnesota. This is an older photo. Currently it's around about 40 people, but the point is it's a pretty small team. And we are limited by manpower, of course, eager for new recruits, which is why I'm going around giving talks like this. Bicep 2 met this guy for 3 years, is now retired. Keck Array is 5 copies of Bicep 2 and is plugging away as we speak. Now, when people hear the name Keck, they have to think of a telescope in Hawaii. But we chose a less hospitable location about a mile north of the geographic South Pole. So here we are standing next to Keck. That's the station off the distance where everyone sleeps over down there. That is immediately adjacent to 90 degrees south. This light show in the sky, maybe you've seen it here in Rochester, but it's basically it's a rainbow through ice crystals instead of water droplets. You see this occasionally. If you look north, you would see the Dark Sector Laboratory. This is home to the Bicep cameras. This is the South Pole Telescope back there, or SPT for short. That behemoth is 10 meters across, optimized for different science schools. We'll come back to that later. This is one of the best places in the world to do this science. There's superb infrastructural support, logistical support from the NSF's Office of Polar Programs. This is one of the driest places on the planet. Just because it's so damn cold there, the old water just freezes out of the air. And that's critical for us because water vapor can absorb and re-emit the very light we want to see, so dry is good. It's also true that the sun rises once a year, and 6 months later sets once a year. Right? So it's a very stable sky to look through that's not being churned up by diurnal variations from the sun. And that's important because that turbulence from the atmosphere would introduce noise into our measurements. Right? So if you look inside these shields, you'd see instruments like this, not too big. This is Keck array here. The reflective thing surrounding people is not a mirror, it's a ground shield that's meant to keep us from seeing the surrounding terrain. These are Zuckler 4 baffles above the cameras, and if you had Superman vision, you could see inside this enclosure, and you'd see cameras like this. About the size of a person here, so just big enough to get the job done without going overboard. That's our mantra here. Right? So it's a pair of lenses made of plastic, opaque and invisible, but transmissive in millimeter. And those are there to function as a spyglass, imaging the sky onto a focal plane below that we stuff full of detectors. This has an aperture behind the objective lens, which at 150 gigahertz, where many of our cameras have operated, that gives us about a half-degree resolution on the sky, just enough to get the job done. Right, the whole thing goes inside of a cryostat, and we use a pulse tube system, or in the case of BICEP 2, liquid cryogens. We chill the optics to about 4 Kelvin, and the point here is that you don't want the camera glowing in front of your detectors, right? You want to reduce the loading on that, because as you'll see in a moment, that keeps the sensitivity high. And in fact, we have very low loading compared to most of our competitors, and so we enjoy much higher sensitivity. The actual detectors in the focal plane get chilled to about a quarter of a Kelvin actually, by an internal helium-3 and helium-4 absorption fridges that aren't shown in this picture, but are there nonetheless. Historically, those focal planes look like this. This is BICEP 1. These are hand-assembled, horn-coupled NTD germanium bolometers, about 100 in total. So these are very similar to what was flown in the Planck satellite we saw on the map earlier. And these in particular are split evenly between 2 colors, sort of near where the microwave background is brightest. It's one of the largest ever made with this technology, and you can see why people stopped. It doesn't use the focal plane very efficiently, and it's kind of arduous and expensive to assemble. That's why with BICEP 2 we switched to this new technology, monolithic detector arrays, much denser packing, you can see here. This was just one color, 150 gigahertz, right? But 10 times the detector count is over here at that color, thus 10 times the mapping speed. In other words, to get the same signal to noise with BICEP 2 as you would want to get with BICEP 1, it takes 1/10 the time. Right? And these are modest priced cameras, all things considered, so why don't I have more? That's what Keck array is. When it was running at all 150 gigahertz, we've since diversified the colors, but at that point in time, it was 50 times the count, that's 50 times the mapping speed. This is what I mean by this aggressive pumping up of our sensitivity. Right, so the focal planes contain 4 tiles, each fabricated by monolithically by my very close colleagues at JPL. We read the detectors, in particular their current, with squid ammeters that you can see down here and up here. Those are purchased from NIST out of Boulder. The pixels look like this. So they are dominated in footprint by a planar antenna array that's used in lieu of a horn to do the optical coupling. If you zoom in further, you can see the sub-antennas of the array. You can see vertical and horizontal slots carved into a metal ground plane. So it's really 2 polarizations, 2 antennas rolled up into one. That metal sheet is used as the ground plane for the microstrip transmission lines, that sort of white spaghetti mess that we use to feed the waves together from the different little sub-antennas here. That's what those beams of this is for us. All that's made of niobium in superconducts, and so it's very low loss.
Can you give us some idea of scales on these photos?
Yeah, no, little JPL was telling me to remove scales, but this is about 8 millimeters across, so that's kind of the size of your thumb. It's on the order of a centimeter, right? And so these things here are about a third to a half millimeter long. Yeah? These lines themselves are a few microns across. So if you pick the impedances in these transmission lines, then judiciously you can sort of choose what the illumination of the slots are, and that actually influences what the beam pattern is. We've actually explored 2 designs. Right, you can uniformly illuminate them. This is what this looks like here. This is the measurement in a test cryostat. That's the far field from a top hat, so it looks like a sink. You got side lobes here, right? And that actually spills onto our stop sum. It's an efficiency hit, but remember the stop is cold, so it's not really a big deal. But perhaps someday you wouldn't use this in the BICEP stop cameras with some other optical design where you don't have as cold a stop. So we designed a different illumination pattern that is Gaussian in shape, so the far field looks more Gaussian. Right? And so you can see over here in this option where those side lobes are considerably knocked down. This is sort of in anticipation of some of the satellite missions that we're currently bidding on. This is also being used in the current BICEP 3 telescope just to see how it works. Right, so there's little filters hiding in the corner. They're pretty full filters. I'm not going to discuss the design much of it, but point out that it's there to prevent our instrument from looking at frequencies where the atmosphere glows, which you would see as where the transmission in black is going down. Right, this is from oxygen. The third one's water. And these are the sort of where the bands are located for different instruments with different colors. The detectors themselves look like this. This is a TES bolometer. That stands for Transition Edge Sensor. It is a release structure, so we've carved out the silicon beneath. And this island is held up by these 6 little tiny legs. So it's a loose thermal contact of the instrument, and in fact is free to be at a higher temperature than everything else, and indeed it is. Optical power enters this thing down one of the transmission lines on one of the legs, and it's niobium, low loss, up until the island, then it switches to gold, which, funny thing for us, high purity gold is a resistor just because the skin depth is so small. That thermalizes the power next to the transition edge sensors, and there's one in there made of titanium that we bias onto for sky observations, about a half of a Kelvin transition. We use lines here you probably can't see. We voltage bias into its transition in between the superconducting state and the normal state, right? This is resistance versus temperature. And you might think naively that if you swing your telescope to a hot point in the sky and increase the optical loading, you would climb up out of the transition, right? But that's actually not the case, because remember the bias circuit is also delivering power, V squared over R. Right, so as you try to dump more power in here and try to increase the resistance, that actually chokes off the bias circuit, thus reducing the current running through there. Right? So as the optical loading goes up, the Joule heating goes down and back and forth. There's a feedback effect. We basically made a knowing detector, and it gives it a linear response over a wide range of optical loadings. Simply those that are hot enough you don't watch superconducting, and not so hot that you saturate and go normal. So we're monitoring the current through these bias lines, and ultimately through the squid ammeters off to the side. And the squids, by the way, have enough bandwidth to allow for multiplexing. We can read multiple detectors through a common set of lines. We use a time domain multiplexing system. We have a set of 32 detectors, and we just read one after the other and repeat quickly enough that we don't alias down high frequency noise into our observations. So you might think this thing might not work so well. It's kind of a Goldberg machine. Actually, it works very well. The green here is showing what the efficiency of the actual detectors are with a load in front where we sweep the temperature. We infer roughly 70% efficiency there, integrated across the band. The end-to-end efficiency of BICEP 2 here is in blue, about 40%. So these numbers are good in our field. This is a plot of noise. So this is noise effective current. The current you would have to look at for a couple seconds to get a signal to noise unity. Blue is a measurement, just looking at the time stream and Fourier transforming it. The solid black here is the result of modeling. They disagree up here because of something called excess noise. It just has to do with the phonon conduction down the legs of the bolometers is hard to model, although I think the physics is well understood. But the actual science bands are down here at 10 to 50 hertz or so. And there you actually get pretty good agreement. And you'll notice that this total here is actually dominated by the solid dashed line. That's photon noise, right? The noise, mostly shot noise associated with the incident photons inherent in the incoming light, right? And the next most important term is phonon noise here, down the legs of the bolometers. And so when you design that thing, your job basically is to pick the conduction down the legs so you can dissipate enough power such that you won't saturate, right? But don't make it so high that this actually comes to dominate your noise, right? So the idea here is that this is limited by the noise in the background, the photons itself. And once you're in that limit, then you can't really make the detector a whole lot better. The only way you can prove this thing is then to put more of them on the sky. Multiplexing helps with that to reduce the number of wires going to the cold stage. The catch there is you have to simply sample quickly enough that you don't alias this noise down to your science channel, and indeed we don't. And then beyond that, you have to build more detectors. And that's where this design comes in, right? This is work that was actually funded by our esteemed fellow Caltech alum, Gordon Moore, founder of the Intel Corporation and of Moore's Law fame. And we like to say we took not only his money, but his idea as well. By keeping everything printable lithographically, we could really scale this up in a hurry. Right? And in fact, between BICEP 2 and Keck, when we were sort of our peak efficiency, we had in excess of 3,000 detectors in the sky at once, between a set of cameras, which is pretty good. Nowadays, we have Keck and BICEP 3 on the sky. These are sort of in a partial state of completion right now, but we're already beyond that at 3,500 detectors. Also, this allowed us to get detectors in the sky before many of our competitors, which is key too. Right? Time detector counter, in some sense, degenerate here. Right? So I'll point out that between these cameras, we've had 8,860 detector years clocked so far. So this is sort of the power of this design. So you can take those noise-effective currents, convert them into ultimately a noise-effective temperature. I won't go through the mechanics of that, but I'll simply remark that this is the temperature that you look at micro K for a couple seconds to get a signal to noise of unity. And so in 2013, between Keck and BICEP 2, we were clocking at 8.5 microcalories a second, which is awesome. Compared to BICEP 1, the previous generation, up at 63. Right? There's a factor of 8 difference there, but then again, there's a factor of 60 difference in the detector count, so it kind of checks out. Planck used the same sort of technology as BICEP 1, albeit in space, so there's no atmospheric loading. We see 20 Kelvin glow from the atmosphere. They, of course, see no atmosphere at all in space. Nonetheless, because they only have a few detectors, they're hanging out here at 18. SPT Pole, our neighbors at the South Pole, right, they're clocking it a bit higher too, and it's simply because they can't make more South Pole telescopes. Those things are giant, they're expensive. Additionally, the actual optical design provides extra photon loading, which in turn boosts the noise. Right, so this is sort of the beauty of this design. So we make maps like this. Right, this is map of temperature. These are Stokes parameters. Vertical minus horizontal is Q, the middle one, and diagonals are the U Stokes parameter. Notice that these have a power of plus or minus 3 microK versus plus or minus 100 for temperature, so it is partially polarized. These on the right hand are null maps. We divide the data in half and subtract. It should subtract away the signal. If it doesn't, you see residuals, you get terrored by the systematics. We pass those tests, and it's really just a map of the noise. And in fact, the NAT you saw a moment ago was extracted from these maps directly. So you can combine Q and U to make the E and B maps, right, with color scales here. Each of these lines in direction tells you the direction of dominant polarization, and the length tells you the excess in that versus the other. And you can see here by I, it's dominated by circles and by asterisk patterns, right? In other words, E-modes, like we described earlier. Whereas the B map here, of course, is dominated by kind of a pinwheel-looking pattern. These are different color scales, differing by a factor of 5, and that number is somewhat important. This is from BICEP 2. Here's Keck. If I have to go back and forth, look at the top panel, you see things are basically the same. We're really nailing that one. The signal to noise about is several hundred. The B, on the other hand, is a signal to noise of around about 10, right? So that you can see the effects of noise, because it looks a little bit different between each of them, although it turns out, statistically equivalent, we've decided. So you can Fourier transform these along the vertical and horizontal axes, and then integrate in rings to get variances, right? That's how you make a power spectrum. And so you get stuff that looks like this. So this is the temperature power spectrum above. E-modes at right, sort of a cross correlation between them. Note the null maps here are shown in blue. So you can see the signal to noise here. It's tens of thousands, really. 10,000-ish on this one, I should say. Whereas this one, you're looking at something that's several hundreds. So we're nailing those. And B, as I advertised before, is sort of a signal to noise of 10-ish. So this is the B spectrum here. Here's a better view. So this is the sort of key plot from the BICEP 2 paper. You have band powers here in these points. Error bars are from simulations, 500 of them, simulating a sky devoid of any gravitational wave or foreground signature. This again is the sort of null map spectrum down here. It is indeed consistent with 0. The null hypothesis is basically just gravitational lensing that again we'll come back and describe in a minute. You can see we're exceeding that by a significant fraction, 5-ish sigma, a little bit more. The best fit pure cosmological interpretation of this would simply be R equals 0.2, a very strong tensor signal. That would be this lower dash curve. The upper dash curve is the sum of these two, so that's sort of the best fit. Now, if this really were just a cosmological signal, this would be a true watershed moment in the history of science. Right, this would tell you that the energy scale of inflation is about 10 to the 16 gigaelectron volts. Nearer, we think the strong force should unify with the electron weak force. Right, this is about 1 trillion times hotter than what you can attain at the Large Hadron Collider. Necessary for that modeling was invoking some sort of bits of quantum gravity. So this would suggest that gravity has to exhibit those properties on a very fine scale. And so it becomes of interest to string theorists. There are community of string theorists who build models of inflation, and they're interested in what is the energy scale of inflation. Right? That can be used to test and even falsify some of their models. And it puts serious pressure on non-inflationary cosmological paradigms, and of course is a point in favor of cosmology. Right, so in these ways, this has been long regarded as a holy grail of cosmology, and anyone who's ever watched a Monty Python movie knows that a quest for the Holy Grail ultimately ends in Frenchmen heckling you, and specifically those who worked on Planck through ESA. So we'll switch to a more appropriate photo here. The dirty secret behind BICEP 2 and Keck up until a year ago is we just looked at one color, 150 gigahertz, with a microwave background is brightest, which gives us precious little power on our own to discriminate between cosmic effects and galactic foregrounds. Now, there was legacy data from the previous generation satellite, WMAP, that convinced us that there's not much synchrotron in our field. And we have a little bit of legacy data from BICEP 1 and a couple of colors that we were able to use to say, well, it looks like it's cosmic, but it wasn't definitive. This is what Planck looked at. These 3 channels here, where synchrotron should dominate. And that's simply because synchrotron is red in the spectrum. It's increasing as you go down in frequency. right? Whereas dust should be strongest in these upper channels. That's blue. It's increasing with frequency. And of course, these channels in the middle where C and B should be least contaminated. So this is actually the key map here, because this is the highest frequency where they have polarization information, and it's effectively a map of dust up there. And this is where our field was, so a subset of what they've looked at. And we can take their map and our map, and we can do a joint analysis. We've done that. We published it a couple weeks ago. And so here's the results of that. So at left, you're looking at our data at 150 gigahertz. At right, you're looking at their data at 350 gigahertz. And this is the cross spectrum between them. And I'll just have you focus on this bottom panel here, or bottom row. This is the B mode one. So this on its own, their B mode spectrum from 350, remember, they're not really that sensitive compared to us, and this on its own is not necessarily confidence-inspiring. You can see our excess power between the different experiments, so there at the degree scale, between CAC and BICEP. This is the cross-spectrum, and this one's important. Let's make this bigger. Right, so this is showing clear excess power and cross-correlation between dust, between the 150 and 350 channels, right? And so it's basically interpreted as dust. It is. And it has the right shape, too. It has sort of an L to the negative 0.4-ish value, which is what it looks like across the sky where dust is brighter, and you can do a higher fidelity measurement, which Planck has done. So you should take seriously that there is significant polarized radiation coming from dust, even though the dust itself in absolute intensity isn't terribly high. And in other words, the point is the magnetic fields are probably stronger there than other specialists in the field have previously appreciated. So the models are, of course, being revised on that. But if you do a joint analysis between these on now what's the likelihood of R, it doesn't peak at 0.2 anymore. Right? In fact, it peaks here in solid black so close to 0 that you wouldn't claim a detection. So right now, the best we can claim is an upper bound of R, less than 0.12, at 95% confidence. Now we're seeing dust, of course, with booming signal to noise. That's a clear detection of dust for what it's worth. We see gravitational lensing at 7 sigma, which is worth noting because many other experiments are also working on that. But this is the tightest detection of lensing from B modes on their own. But the real question here is whether this residual is real, right? We need to narrow the error bars to see whether there's anything there or whether it's just a fluctuation in our experiment, right? So we can't do this just with Planck on its own because we're limited by the noise in Planck. That's what the upper curve here is showing. Basically, signal to noise is a function of frequency for the band that we care most about, L of 80, where the peak should be. Here's our noise down here, at very low, a factor of 100 down. The cross analysis, of course, is the mean between the two of them. But the point is, so Planck looked at maybe 100 times more sky than we did, right? But that doesn't excuse that factor of 100, that only explains a factor of 10. So this really means that our technology here in our experiment is a large technological improvement over the previous generation, right? Despite the fact that we're on the ground and have to deal with the atmosphere, we're still beating them in that metric, right? So that's why we put other cameras on the ground. We have BICEP 3, which is the equivalent of 10 BICEP 2s, but all at 100 gigahertz, much larger field of view, more detectors. It's currently only half complete, so right now it's about 5 of them. That's mapping away, or will be shortly. This is the 5 cameras. For the past year, we've had a pair of them at 100 gigahertz, mapping away, giving us relatively deep maps at that color. We just recently installed a pair at 220 gigahertz to give us more direct sensitivity to dust. Right, so these are on the sky. This is first light from BICEP 1. Sorry, 3, I beg your pardon. It's a CMB map. Likewise, for KEP 220 gigahertz, this is all very preliminary, but the point is we're up and going. I'm beginning to observe very soon. We also launched the SPIDER experiment this winter out of McMurdo on the coast of Antarctica. So by virtue of being further north, they can see a much larger part of the sky than we can see, shown in gray here. This means they can have access to more modes in the sky. And also not being right to the ground, they don't have to do as aggressive filtering to their maps. This has 6 cameras, half at 150 and half at 90 gigahertz, or 100 gigahertz or so. But they're basically BICEP 2 style cameras. So this is a video of the launch with some audio. So this is the balloon that will lift this payload up to about 120,000 feet. By virtue of being at such a high altitude, right, the atmospheric loading, instead of being 20 Kelvin, winds up being around about 5 Kelvin, so it's much dimmer. Right? So the noise levels of these instruments go way down. And that means, instead of mapping for years, over the course of a couple weeks, you can see their flight path here, started on January 1st, over the course of 2 weeks, right, this experiment was able to get maps that rival ours in terms of signal to noise, just by not having the atmosphere blowing above you. Additionally, this is a huge technological leap forward. This demonstrates that this can be run semi-autonomously, right, with very little interaction from human beings in this sort of format, which is demonstrating that our team, and more generally the field at large, is approaching technological readiness to putting this sort of instrument in space, in a satellite mission, right? So this launch here, in that sense, is very important for us as a community and, of course, our team directly. And indeed, you really are effectively in space. Here's a photograph from Spider looking down. This is the coastline of Antarctica. You can see the curvature of the Earth. You can see the atmosphere. You're above most of it. Right? So this is very exciting as well. I think looking a little bit further forward, we need to find places to put these cameras. Chile is an obvious choice. In the rain shadow of the Andes there, in the Atacama Desert, it's very dry. Almo's already set up. They're building up infrastructure. And there are many CMB experiments there. We're a little late to the party, but then again, our instrument's pretty good, so we can catch up. This is one of my priorities in the next few years. It also would open up the opportunity to collaborate with my old team from Berkeley on the polar bear experiment. And that's interesting because they had access to this lensing B-mode curve by virtue of a slightly larger aperture. Right? This is a non-primordial B-mode effect. The picture is that photons pass by a large-scale structure that looks like this in simulation. Bright spots are overdoneness of dark matter. The photons don't go in a straight line, though, right? They sort of duck in and out of the gravitational wells that contain that large-scale structure. Right, so if we change the color scale here and then we rotate back, you can see that the photons are actually doing sort of a random walk along these straight line fiducials. So if you cascade many of these things, there's about 50 of these patches in between us and the last scattering surface. Right, that ultimately gives rise to sort of arc-minute deflections, the patterns in the microwave background. So if you turn lensing on and off, and if you guys squint at this figure, you will see these features moving around at sort of a 1/10 of a degree scale, arc-minute scale, right? So this is not a birefringent effect. It doesn't rotate polarization states, but it does disrupt the underlying temperature pattern. And so it has the effect of taking what would have been a predominantly E-mode signature at the arc-minute scale and fouling up that symmetry to force it to be a mixture of E and B. That's the genesis of this green curve here. Right, so getting a handle on this is actually important because in principle you can undo the effects of lensing through an algorithm known as delensing. And so if you constrain tensor modes down to a certain level, down to basically where the lensing is dominating, you have to invoke some of these algorithms to push down to lower levels. And you can kind of get a sense of how that might work. You know, you don't get to turn lensing on and off in practice, right? You can see these deflections, but you can reconstruct that deflection field because this, and I won't go through the math, it introduces correlations between different angular scales that would not be present from primordial effects. And from that, you can figure out the lensing potential and partially undo this. It's also interesting in its own right because it can tell us something about neutrinos. Right, so this is, again, is going to be a small scale effect, but thus you need that larger aperture, you're stuck with it. So if you want to scale up your sensitivity, you have to use your instrument more efficiently, and you have to receive more modes entering your camera than we would, for example, with BICEP telescopes, which has pushed people towards these so-called multi-chromatic pixels, where each detector receives not only two polarizations, but multiple colors, ultimately to help goose up the sensitivity and also to help control performance. Right, so if we look at this figure again, and if you relax your eyes, right, you will see that it's kind of breathing a little bit. What you're looking at are correlations between the deflections, and they're present kind of on a degree scale level. And if you squint, you kind of see it, or don't squint, just relax and look at it. So what this means is if you could extract that deflection angle and make a power spectrum, now in units of radians squared, you'd see this sort of peak at the degree scale. And what you're really looking at there is the lenses halfway between us and last scattering, subtending on the order of a degree or two there. And this is interesting because neutrinos can impact this. Neutrinos have a mass. We don't know the sum of the masses yet, but it's quite small. That means that they can cluster gravitationally, but only on the largest physical scales. On tiny scales, they just free stream away. So there's a Jeans length that's a function of the sum of the neutrino masses, and that can impact this curve, right, by suppressing this effect on small scales as you crank up the sum of the masses. So this is showing a fractional change on the order of a few percent of that curve you just saw, and you can see differences here between zero mass going up to 150 millielectron volt sum. Now, cosmology tells us this has to be less than something like 230 millielectron volts. We've already constrained it that way. And then the neutrino oscillation experiments tell us the differences, 9 and 50 millielectron volts. That doesn't tell us, however, what the hierarchy is. It could very well look like this, with two heavies and one light. Right? This is an open possibility. So by doing this measurement, which is within our reach in the next few years, we can, in principle, rule out the possibility of inverted hierarchy and make progress on this problem. And now, in principle, you could do that analysis from temperature alone. I just showed you simulations of temperature with lensing on and off. And in principle, you can extract that information, but the catch is that you would ultimately get confused by a noise floor, a sample, a variance floor that the microwave background itself presents in temperature. Right? Ironically, it would have been better if the microwave background weren't there in the first place. And you can almost arrange for that because remember that at arc-minute scales, there's no B modes from primordial effects. And so if you rely upon B signals, then you can actually go a lot deeper, put tighter constraints on it. The catch is that to make use of that, you really have to get the noise in each pixel of your map down to about 3.5 micro-K in each arc-minute scale pixel. Now, BICEP 3 and Keck and those other experiments, we're already actually at that level. we have 57 nanokelvin per degree scale pixel, which translates roughly to that, but that's cheating because we don't have the resolution to see those deflections. The experiments that do, though, that are sort of the lead are polar bear in the Atacama Desert. That's about 2.5 meters across in primary, so bigger than our 30 centimeters. This is the South Pole Telescope, which is about 10 meters across. These guys have kind of competitive levels of numbers of detectors as well as their NETs. And they can currently think they can strain down to 100 million electron volt levels, which is interesting against the constrained parameter space. But they're not really quite at that level yet. Now, polar bear drilled deep on one patch of the sky to make a claim of seeing the first lensing effects from D modes. But that doesn't really count. You need to look at a large patch of the sky, so you need higher sensitivity. And to get a sense of how to do that, here's the focal plane for polar bear, right? Similar cryogenics SOAR additive as I described earlier. This is the antenna, the tic-tac-toe pattern here. There are 2 slots for polarization, so 4 in total. There's filters, there's TES bolometers, it's similar. This is a much smaller antenna, so they have a huge beam, right? Whereas ours have a larger area, so it's a finer beam. That's okay, we can put little contacting lenses on top, and that sort of increases the gain so you can match the telescope optics. So that's the idea here. Right, to increase the sensitivity of this camera, polar bear has the money to buy a couple more, so they're reproducing 2 of them, but they're not going to make 10 of them. So you really want to use your focal plane as efficiently as possible, which means to receive more modes here, and one way to do that is to increase the bandwidth. Right, so believe it or not, the most straightforward broadband generalization of the tic-tac-toe pattern is this asymptotic spiral, known as the sinuous antenna, which was the centerpiece of my doctoral work. This is a 4-armed antenna, so it receives the 2 linear polarizations through opposite arms, and it's self-similar. As you zoom in and out, it looks kind of similar. That gives rise to its wide continuous bandwidth, limited only by the inner and outer terminations setting the upper and lower band edges. Right? Once you have that broadband signal coming down this transmission line, you can then partition it into narrow channels. So for example, for polar bear, they'll be using diplex pixels, 90 and 150 gigahertz, sort of split here. This is a prototype pixel, so they're a little bit off where you ideally want them. These are the beams, right? So you can see 90 is wider than 150. And that makes sense because you have a fixed lenslet that you're still putting on top of this thing, but the wavelength's longer, so the gain has to go down a little bit. That's okay, though. You can put a cold stop in your system to spill onto. You still control the optical performance. You still gain considerably in sensitivity. SPT wants a 3-color version, so we'll get him a 3-color version, 90, 150, 220. Again, this is a prototype version. You can see the beams look nice and circular, of course changing the scale. You can see the 3 channels here measured with spectroscopy as well at those colors. That's a work in progress. Anyway, this is going to be used by SPT3G, supposedly in the next year, although it might take a little longer than that. Polar bear and Simon's Array. EBEX is a balloon experiment that will fly with these. Lightbird is a Japanese Space Agency satellite, and they're planning on using this design as well. To throw out some numbers here, there's 15,000 detectors that will be present in SPT3G. And the number to take home is that over a couple of years, over basically the field I just showed you from BICEP, they should be able to get down to 2 micro-K noise in their arc-minute scale pixels. In other words, enough to constrain some of the massive neutrinos, it turns out, down to around 60 millielectron volts. So they have a chance of testing which of those hierarchies is true. So I want to point out here that this is work this design that I dreamt up and prototyped and tested and demonstrated as a doctoral student. Not so much to brag, but to point out that as a student with a good clean room, such as here, right, you can try out these crazy ideas that you couldn't necessarily do in a national lab, right? And once it's working, you can then work with other teams and sort of franchise it to have quite a bit of influence. Okay, so I want to turn to the last topic here, which is low Z cosmology. Lower redshift cosmology. And so now that we're not so much focused on the last scattering surface, right, but rather multiple sort of planes in between us and last scattering, right, now we not only want to look for anisotropies, differences in power in different directions, we don't just need an image, we also need to do spectroscopy at the same time to figure out the redshift, the distance to those distant points, right? So this calls for getting a different type of detector design. And so I'd like to motivate this through reionization. This is a timeline history of our universe again. This is recombination here at the left. So matter becomes neutral. Of course, it's falling into gravitational wells. And eventually, early quasars begin to burn and reionize the surrounding medium, which you're seeing kind of here. Nowadays, of course, it's ionized. This is an area that we actually don't know a whole lot about. We don't know the details. In fact, the decadal review for astrophysics, while not studying this as a priority, had kind, encouraging words to say about the thing seen here. It's useful to have sort of a picture of how this might look in the back of your head. This is a hypothesis. Right? This is showing the neutral hydrogen as a function of time in a large 10 co-moving megaparsec chunk of our universe. And initially it's all blue because it's all neutral hydrogen, but as reionization begins, you see these cavities begin to open up, which are presumably where quasars are beginning to burn, pump UV photons into the surrounding medium, and induce ionization. And so early on, right, you don't see a lot of intersection between these regions. Right, they're sort of isolated, and it proceeds at a modest pace, but eventually they do begin to overlap, or so we suspect. And they share photons, and it enters this more accelerated, we think, percolation stage, where it proceeds in earnest. And so these voids you're seeing are where the hydrogen has been ionized, so ionized hydrogen, but there's no neutral hydrogen. Right? So this is sort of a picture that we have in mind for how reionization might proceed. By the end of it, most of the neutral hydrogen in our universe is now trapped in galactic structure, or maybe these filaments in between. This is just a guess, right? We don't have any data directly to substantiate this. We have ideas of when reionization began, when it probably ended, or at least where a midpoint was. We know roughly what its duration had to have been from indirect measurements. You know, we'd like to reproduce that video experimentally and learn more. Right? And there's a number of different proposals on the table, but they all basically involve a similar idea, which is that if there is some gas during that time that can emit a specific line that we know about, right, we can map on that line. Right? We can also use the redshift of the line to infer how far away the radiation is from us, or how far away the source is. Right? So the technique known as intensity mapping. And the goal isn't to resolve individual sources, but rather to sort of use this glow to trace the underlying structure that's forming. So this particular example is pretty well known. A lot of people are pursuing it. It's a 21 centimeter transition in hydrogen. Right? So it's down sort of in the kind of microwave radio range. And it winds up redshifting from the epoch of reionization into sort of like the 100 to 200 megahertz range. And so this is just a simulation here, really a cartoon of still frames from that video you just saw. So right at the beginning, voids begin to open up, right? And eventually by the time you get to the end, it's all consumed. Right? So this is one way of approaching this, and one that's under active development by many teams. At Caltech and JPL, we're interested in an alternative approach using ionized carbon, right, C+. And this is alluring here because it's very bright. It's 1% of the volumetric temperature of star-forming galaxies. So it's a sizable chunk of it, so we can see it from far away. And this is meant to be a complement to the neutral hydrogen map, so we would really use the data in conjunction with those other teams. Another nice thing is this 158 micron line here, this hyperplane line, gets redshifted from reionization into an atmospheric window of 200 to 300 gigahertz, where we can build a dish on the ground through the atmosphere. So this is simply showing an example of something that's been identified as a potential high redshift C+ line coming from a redshift of about 6.3. So there's optimism to think that we can see such a thing. Right, so this is, I'll go into some of the experiment designs in a second that we're working on, but this is sort of a projection of what we think we could do with the first generation experiment. This is showing a power spectrum. So this is power from a map versus, in this case, wave number, similar to what you were looking at earlier. And this is a model, right? This sort of upward trend at the upper right, that's basically shot noise of the galaxies themselves, intrinsic variability in their brightness and their number count. When you get down here, you see this sort of bulge that's basically the onset of clustering. The reason for this wide band here and these sizable error bars is we actually don't know a whole lot about the metallicity of these very ancient structures. So that can influence this in some way. And so there's actually a wide range of uncertainty in what we think we would see. So one of the first goals of our early experiments is to see if there's anything to this. You can build other models shown in red and green here. I don't want to go into the minutiae of how the models are constructed for lack of time, but simply to say that there's a lot of parameter space to explore. Orange here is a different type of challenge. This CO, rotational modes at lower redshift, right, that nonetheless redshift into our band. These are sort of interloper lines that can confound us in principle. We think we can mask them. In principle, you can mask them with maps and catalogs of galaxies. And so these dashed lines here are showing different levels of suppression from different masking techniques that we've explored in simulation. This may be interesting in its own right, as I'll allude to in a minute. Long term, we want to, as I mentioned earlier, cross-correlate our data with hydrogen data, 21 centimeter. And we think this is quite powerful if you do a cross-correlation, because it can be used to trace the bubble size as a function of redshift, right? So imagine looking at a very large region in our universe, where you can see some of the bubbles, right? So what you'll see is hydrogen in the blue regions, and then in the cavities you won't see hydrogen, but you will see carbon there. That's where the carbon is being produced. So you expect these to spatially anti-correlate. Of course, on a small scale, smaller than the bubble, you're either seeing nothing but carbon or nothing but neutral hydrogen. Right? In that case, the correlation should relax to 0. And the transition here should sort of trace the bubble size as a function of redshift. That's how we would experimentally reproduce that video that we were just describing. Right, so that's a long-term goal we'd like to do with these experiments. In the short term, we're building something called TIME. TIME is Tomographic Ionized Mapping Experiment. We're actually calling it TIME Pilot, meaning it's the first installment. This is going to basically use a grating spectrometer established through other experiments that we've deployed. Broadband light will enter the spectrometer, seen in sort of this white color here, and then the tooth grating down here will split into different angular positions. We line that with TES bolometers. Bolometers, by the way, that we have developed for another experiment, BLISS, that we've sort of stopped pursuing. But the point is that all this is technology that has some heritage. Right, we've already started building this thing. Here's the cryostat in the basement down at Caltech, and are beginning to build some prototypes. The goal was to put this in Mauna Kea at the JCFT in 2016. We're working with Asia A, who have a large sort of role in that telescope now. The goal here is to have 18,000 detectors split between sort of 32 spectrometers, covering the 180 to 320 gigahertz range with modest resolution. But that should be enough to begin to explore this and see if there's anything to it. The scan strategy actually is just going to be a slice back along a sort of a line in the sky, so very deep on one axis, so we can concentrate our sensitivity to a specific set of modes. Longer term, we'd like to shrink this down. Those things are big, those spectrometers. We'd like them the size of our thumb. So we're beginning to develop that technology as well, which I've been directly involved with. So this is the antenna that you might print. There's multiple ways this will go in the future, but this is a prototype. And to demonstrate this would work, power goes down a microstrip transmission line, just like before. But now, instead of a single filter, you have a bank of filters, really resonators, that couple power onto a set of detectors. So if you zoom in, power will come down the microstrip line here that I'll highlight in yellow. It'll then go by these little hairpin sort of staple resonators that are lambda over 2 long. Right, that's where they'll resonate. Right, that'll couple power then to another set of lines. This is a little complicated here. We've simplified it in more modern designs. But this extra circuit to the right here is meant to couple power to the TES, which is over to the far-hand side on the right there. You can control the width of these lines, the Q of these lines, by basically picking the separation between them. That separation determines the Q sort of above the level of Q that you would expect from loss. All right. So anyway, this is a prototype design we've done between 200 230 gigahertz, series of channels. These numbers here are the intended ordering of those channels, so they're in the right order. They're a little snaggletooth. It's an early design though. We have some ideas on how to improve that. There's maybe some evidence of standing wave effects in here as well. Again, that's active research. The efficiency of these is pretty high, around 15 to 20%. It's not phenomenal, although we do know that a lot of the loss is coming from the actual filter stack we have in the cryostat. So this is a very promising technology, we think, for leading the way on this. So I'm basically out of time here, so I don't have time to talk about my ideas about how to study dark energy, so I'll just flip through these things. And I will simply remark, if we want to talk about that, we should. Nonetheless, there are pretty awesome science schools that we can approach, right, that are sort of coming of age, or in the case of this stuff is sort of really happening as we speak. But of course, behind this this awesome science is technology that's enabling it. Thank you very much.
Okay, I think we have a few minutes. Are there any questions? Any questions? Oh, there's one.
So if you don't detect the carbon-2 line, are you going to, I guess number one, are you going to know it? And number two, can you put any reasonable limits on the metallicity at z = 6 or whatever it is? Can you turn the problem around, in other words?
Yeah, I think you can turn it around. I don't know the numbers off the top of my head. Yeah, I think you can make statements about the metallicity based upon a detection or lack thereof of that signal that you're looking for. My fear is that it's more complicated systematically, because I do expect CO to confound us. I'm not entirely confident that the galaxy catalogs will get us out of the woods on that. So, one scenario is that we wind up waiting for a while to find some decent weighting, but we wind up having to do some secret analysis later on once we have a decent neutral hydrogen map of our field, right? Because through that cross correlation, I think we won't see the CO. The CO will fall out of that cross correlation because it's an entirely different redshift. But that's actually where I envision the greatest challenges coming from. Not so much, hey, we don't see something, but rather convincing ourselves robustly that we've seen that and we've appropriately controlled the foregrounds. That's